A polyacrylic acid grade can pass early evaluation and still behave differently in production, even when the molecular weight on the spec sheet is identical. That can surprise teams. In electronics applications like chemical mechanical planarization and wafer polishing, the issue often isn't the average molecular weight, but rather how that molecular weight is distributed. Molecular weight is usually reported as a single number, which is an average. That average doesn't tell you how the polymer chain lengths are actually distributed throughout the material. Two PAA grades can share the same reported molecular weight and still have very different distribution profiles. For example, one might contain a higher fraction of shorter chains while another might have a broader high molecular weight tail. In CMP applications, those differences influence how the polymer adsorbs to the wafer surface, how the slurry behaves, and how consistently material is removed during polishing. Because most specifications focus on the average molecular weight, those distribution differences can go undetected during incoming inspection or early evaluation. They show up later as polishing variability, surface inconsistency, or unexpected performance drift during scale-up, once the material is inside a tightly controlled process window. When they appear, they aren't always easy to trace back to molecular weight distribution, especially when the average value looks correct. That's why electronics-grade PAA isn't defined just by hitting a target molecular weight. It requires control over the full distribution profile and understanding how that profile behaves in real process conditions. If you're qualifying polyacrylic acid for CMP or wafer polishing, it's worth asking not just what the molecular weight is, but how it's distributed and how tightly it's controlled. For a deeper technical breakdown, we've linked the full blog post in the description.